I'm going to be talking about micrometeorites as a new proxy for CO2 in the Archaean. There we go. So we're all pretty familiar with CO2, right? We've just heard about it a little bit. And on the modern Earth, right, it's a great greenhouse gas. And even though it's just a small fraction of the total atmospheric mass, it plays a very important role in controlling the surface temperature on the modern Earth. And of course, this has been true right, throughout Earth's history. And we just heard a little bit about the Archaean, right? And that CO2 levels were likely much higher then because the Earth wasn't frozen at that time. But in order for it to have this liquid surface, right, we need more CO2 to have that higher surface temperature. But exactly how high the surface temperature was is something that's still debated. And we have those sort of two schools of thought that we saw in the previous talk, where we have this low temperature regime, which for our purposes is under 40 degrees C, and there's isotopic evidence and phosphates to support this. In addition, you see evidence for glaciations, potentially in the Archaean, which would support at least a transiently cool Earth at that time. On the other hand, if you look at oxygen isotopes in cherts, you see a much warmer temperature between maybe 55 and 85 degrees C, and you also see that reconstruction of thermostable proteins in the Archaean supports this high temperature early Earth. And there may be evidence for a low viscosity ocean at that time, which would further bolster this high temperature claim. And a big part of the uncertainty here is how much CO2 was available at this time on the early Earth to warm the surface. And of course, right, we care about this because this is when the first evidence for life is showing up, so we'd really like to know what these surface conditions were like and how much CO2 was there can help answer that question. Of course, constraints on CO2 aren't great for the Archaean. And if we look at the proxy data, we see that we have on the low end about 10 to the minus 3 bar, and on the upper end, close to 1 bar is our estimates as we go back in time. So we have almost 3 orders of magnitude between our upper and lower bounds on CO2. And models, which you see this nice model here from Chris Sanson-Totten, who has made his way into all the talks so far. You see this nice model prediction from them with their model mean in the black curve here. And so CO2 is increasing with time. And then the uncertainty of their model is shown by the gray shaded region. So with both models and the proxy data you see here, there's a great deal of uncertainty. Now, fortunately, this is where micrometeorites might be able to help us. And so that's what you're looking at here. These are 4 micrometeorites that were extracted from a 2.7 billion-year-old limestone from Australia. And if you're not familiar with micrometeorites, they're essentially just sand-sized space dust that falls to Earth quite often on the modern Earth and probably has throughout Earth's history. And in particular, when I say micrometeorites in this talk, I mean iron-rich micrometeorites, so a special type. And that's what you're looking at here. And the reason we care that they're these iron-rich particles is if you take metallic iron and you put it into the atmosphere very rapidly, it will melt. And when you have molten iron with an atmosphere of like CO2-rich or oxygen-rich, it can oxidize. And that's what we're interested in. And in addition, as you can see from the beautiful preservation of all 4 of these, that are 2.7 billion years old, clearly these iron-rich micrometeorites are able to stand the test of time and show up quite nicely, even on the Earth today. So if you were to look at these 2.7 billion-year-old micrometeorites, you would see that they were highly oxidized. So they contain magnetite and wustite, and they actually look remarkably similar to modern micrometeorites in terms of the amount of oxidized iron in them. And so this has led to speculation that the Archaean Earth had an oxygen-rich upper atmosphere to explain the presence of wustite and magnetite, these oxidized iron species. But if we look at oxygen through time on the Earth, as we see here with the present Earth, and we go back in time, these micrometeorites are preserved right around here, where the total oxygen in the Earth's atmosphere was quite low. And surface proxies constrain the atmospheric oxygen to below about 1 part per million, so basically a trace gas that's non-existent in the atmosphere. And even proxies for the atmosphere at altitude constrain it to a fairly minor component at best. And this is an upper bound in the upper atmosphere of a fraction of a percent. And if we take that with our understanding of atmospheric mixing, it seems perhaps unlikely that we could have had modern levels of oxygen, so an oxygen level up here in the upper atmosphere, and nothing at the surface in the Archaean to oxidize these micrometeorites. So that's sort of where we started with this work, is if oxygen seems perhaps unlikely, then CO2 is maybe a better choice to oxidize these micrometeorites on the early Earth. And so that's what we wanted to look at. Can we build a model where if we take a micrometeorite, and these are examples of modern micrometeorites, can we take one of these and can we measure the fraction of metallic iron, which you see here in the white region, and the oxidized region here is shown in gray? Can we measure that and then back out what the oxidizing power of the atmosphere was that these particles entered in? I just want you to make a mental note of what these look like, because you're going to see a model simulation in a moment where we're going to reproduce micrometeorites that look just like this in cross-section, where you see an unoxidized metallic bead in the center and then an oxidized rim around it. So of course, we started with the modern atmosphere. So we have a known atmospheric composition, and we can collect modern micrometeorites like you just saw, and then we can try and back out the atmospheric composition. And so our model starts out with the assumption that we have a pure iron micrometeorite at the top of the atmosphere, and then we pick a radius for that particle, we pick a velocity and an entry angle, and then we drop it into the atmosphere essentially and see what happens. And so we start with this very fun animation at 190 kilometers above the Earth's surface, and there's our beautiful particle. And before I run the simulation, I just want to point out some of the parameters that we're going to track, because it happens pretty fast. So we're going to be looking at the particle temperature, the velocity, and it's starting at about 12 kilometers a second, so it's going really fast. This is about a 50 micron radius particle, and its iron fraction is at 100% by assumption, right? We're starting out with a pure iron particle, and then we're also tracking the altitude. And so the cutoff right here, this is the cross-sectional area. And so you'll notice that it's all this dark gray, which is matching the metallic iron. So this is showing you the composition is currently 100% metallic iron. And as we run this forward, you're going to see this shrink down to that central bead, similar to what you saw for those modern micrometeorites, and you'll see an oxidized exterior form. All right, so we'll run it forward. There we go. And so you'll watch that the temperature is pretty minimal, and it's going to climb really fast, and you'll see this particle get white hot and melt as it exceeds 2,000 degrees Kelvin and warms up. And then if you watch, you can see the cross-section shrinks, and we end up at the end of our simulation with a particle that looks like this. So you're seeing this essentially running in real time here, where we have 15 or so seconds from start to finish, and the particle is only molten during these orange portions of the curve here. So just a few seconds where you go from your iron particle and you very rapidly melt, and you produce something that looks like this as you oxidize the exterior. So we did this for the modern atmosphere, and we essentially recorded this cross-section right here for each of our particles. And then we took that and we binned it on the horizontal axis here, based on that, the size of that iron bead in the center, right? The fraction of the area of the cross-section particle that was this metallic iron. And when you do that for the modern Earth, we generated a histogram in blue right here. So 500 randomly generated particles, and we see that if we took the average cross-sectional area, we get around a 0.3, which is that iron bead in terms of area. And then we can compare that to modern micrometeorite data, which is shown in orange, collected from Antarctica, and you'll see that we do a pretty good job of reproducing the distribution and the mean of our model, and the data mean agree quite nicely. So the next step then was to apply this to the Archaean. And so that's what you see here, and this is the main result from our model, where once again you're looking at that fractional area of the micrometeorite, and this black curve here is showing you that Fe fractional area mean. So up here, low CO2, which is then increasing on the horizontal axis. So as you increase CO2 concentrations, you see this monotonic decrease in that Fe fractional area that you would expect to find in collected micrometeorites. And this is pretty exciting, right? Because you could go out and find a couple of micrometeorites, you section them, and you measure that Fe fractional area in your section micrometeorites, you find the mean, and then you basically just come over to the line, and you can drop down and back out the CO2 concentration of the atmosphere at that time. And that's exactly what we did with the 2.7 billion-year-old micrometeorites, which is shown by this orange dot here. You come down, right? We just went over, and so you find, it's about 64% CO2. The error bars are quite bad on this measurement, and I'll get to that in a moment. But there's one other thing that I want to point out here, which is this dashed blue curve along the bottom here that starts to come off zero at around 70%. And that line is showing you the fraction of micrometeorites that were fully oxidized. So if you think back to the simulation, where we had that iron bead in the center shrinking, well, if you encounter enough oxidant, then you can actually oxidize the micrometeorite all the way through. And in our model, that happens right around 70% and higher in terms of CO2. You start seeing these fully oxidized particles. So what does that tell us about CO2 in the Archaean? Well, the reason that the error bars are so bad on that orange dot that you see here is that we only have two measurements from the Archaean data to constrain that point. So we have really big uncertainties on that. But this is something that could be easily addressed by collecting additional micrometeorites. Fortunately, there were fully oxidized micrometeorites in the 2.7 billion-year-old samples. And so we can get a tentative lower bound on CO2 in the Archean of about 70% of the atmosphere by volume based on the presence of those fully oxidized micrometeorites. And I put some nice emojis here to say that one is not great, and we'll get the green smiley. That one is pretty cool. All right, so these improved CO2 constraints are really important for the Archean Earth. We can not only potentially address the temperature question for the Archean, so if we took our sort of 70% atmospheric CO2 estimate, and if we assume a paleo pressure of about 0.5 bar in the Archean, then with a very simple climate model, we can estimate about 30 degrees Celsius for the surface temperature as a potential upper limit there. But these improved constraints can also help inform our understanding of exoplanets. If you think of the Earth as an analog for sort of a different habitable world. And in addition, this is when the evidence for life first appears on Earth is during this time. And the CO2 concentration of the atmosphere plays a really important role in controlling surface temperature and the pH of the ocean, which we'd really like to know for this period of Earth's history. So from this model, right, we see that we could potentially get much better constraints on Archaean CO2 if we go out and collect more micrometeorites. And in addition, this same technique could actually be applied potentially for the Proterozoic, where CO2 may remain the main oxidant at altitude, and so these micrometeorite oxidations could still be sensitive to total CO2 concentration in the atmosphere and be able to provide insight there. But for all this to work, we need more micrometeorites, so we need people to go collect them and measure them to put into this model. Thank you.
Thank you, Owen. We'll take questions.
Yeah, I think this is occurring at about 100 kilometers, is that right?
Yeah, so these are melting between about 70 and 90 in the modern Earth's atmosphere.
Now I've been told that under the troposphere you have mixing of the gases, but as you get further up you get some segregation density. And CO2 is rather heavy, so I would have thought that there was some type of gradient in the CO2 concentrations as a function of height when you get to those altitudes. The other problem I have is you said half a bar. Presumably, there's an uncertainty on that. It could have been, I don't know, 2 bar, 10 bar. I'm not sure how large it is. I'll have to ask somebody else. But that also increases the error bars, I suppose, on your data.
Yes, so both those great points. So to address the question of mixing first, so on the modern Earth, right, even though the troposphere, right, is where you have turbulent mixing, you have convective mixing, so it's very rapidly mixed, you still have mixing up to about 100 kilometers, which is the homopause region, and the atmosphere remains well mixed below that due to turbulent mixing of breaking gravity waves. So you get that from airflow over, say, topography or from jets in the atmosphere. And that would occur throughout Earth's history. So even in the Archean, we would expect the same thing. So these are melting at a pressure below that well-mixed height. So the atmosphere should be well-mixed up to the altitude where these are melting, regardless of how much CO2 is in the atmosphere. And then to address the second point of the total pressure of the atmosphere, that is a great point to bring up. And so this technique is not sensitive to the total pressure of the atmosphere because it's only sampling the upper atmosphere, essentially. And so if you had a half-bar atmosphere, then the altitude at which the micrometeorites melt would shift closer to the surface, but the overall reaction that's occurring would be identical. And the same is true if you put a 10-bar atmosphere, then they would be melting at a higher altitude but at the same pressures. And so we can't constrain the total surface pressure, so you need an alternative method to constrain total pressure, and then this can give you the fraction of the atmosphere that's CO2.
I would have thought that when you change the pressure, it's true that you oxidize. You could oxidize at a larger. When you're higher, it could be a longer time. For example, you showed a certain period, you said it's only molten for about 2 or 3 seconds. Does that number depend on how high you are? Which would then depend on the pressure in the way you just described.
Yeah, so we did test it in the model, and it's a very minor effect. Really, the only difference is sort of the gravity term with scaling. So, off the top of my head, I don't know exactly where the corresponding level in a 10-bar atmosphere would be, but presumably it's not a huge difference in total altitude. And so we didn't look at a 10-bar. We looked at actually just decreasing pressure and that effect. But it's definitely something that could be considered.
Do we have time for one more? Okay. So rather naive question. In your physical samples, the iron core that's left over seems to be shifted in one direction.
Yes.
Do you think that there's a possibility that some of these could just fully segregate the remaining solid core from the molten portion, and that's actually what you're seeing in some of these fully oxidized samples?
Yes, so that is definitely a possibility that the sort of the more dense iron bead could separate from the micrometeorite. And so Matt Genge actually has a number of papers on that where he speculates that that isn't likely. So they don't think that that's occurred because you don't see that often when you're looking at micrometeorites. You don't see ones that are sort of partially separated, and you would expect maybe when it separates that the central bead would maybe split, and so you'd end up with other features. I'm not super confident on that, but I do believe that that has been somewhat addressed, but it is definitely a concern that you could have the beads separate. So actually, that's why in our model we don't consider fully oxidized micrometeorites. We're only looking at ones that still have the metallic bead, so that way we can be certain that we're looking at, well, as certain as we can be, right, that we're looking at a partially oxidized micrometeorite to back out that ratio.
Cool, thanks.
Mm-hmm.